Hi everyone, welcome back to my YouTube videos. So in today's video, I'm going to give you one more example of application in which we have to deal with symmetric probability spaces. And more precisely, so I call this video rooks on the chessboard, and here is more precisely the problem. So we assume that 8 rooks are randomly placed on a chessboard, and we want to find the probability that none of the rooks can capture any of the other rooks. So if you know a little bit about chess, a chessboard is an 8 by 8 grid, and rooks can only move any number of squares, but only horizontally and vertically. So you can reformulate the problem by saying, so placing 8 rooks uniformly at random on an 8 by 8 grid, what is the probability that no 2 rooks are on the same line, the same horizontal or vertical lines? So to solve the problem, we are going to, instead of only writing equations, I'm going to use a little chessboard, and we are going to try to put those pieces on the chessboard. So let's go to the chessboard now. So here is our chessboard, and I'm going to use those red pieces from another game called the Connect 4 to play the role of the rooks. So the first step is to compute the cardinal of omega, which is basically the total number of outcomes in our symmetric probability space. So that's going to be the total number of ways we can put 8 rooks on the chessboard with no restriction. So of course the problem is that to count the number of possible configurations, that depends on whether we assume that the rooks are distinguishable or not, and I'm going to give you both answers, and we are going to see eventually that whether you assume that rooks are distinguishable or not does not matter. It matters when you count, but it doesn't matter when you compute the probability. So first, let's assume that the rooks are distinguishable, and by that, in fact, what we mean is that we are going to place the 8 rooks sequentially. So we look at the number of possible ways we can put rook number 1 and then rook number 2 and so on. And so for the first one, we clearly have 64 possibilities. So let's put it here, for instance. And then for the second one, we have 63 squares left. So 63 possibilities for the second one. For the third one, we have obviously 62 possibilities. Let's put it here. For instance, you see here, I intentionally put those two ones on the same horizontal line to insist on the fact that we are not looking right now at the outcomes in the event that no 2 rooks are on the same line. We just look at the total number of outcomes. So I think you understood the pattern. Eventually, the total number of ways you can put those 8 rooks on the chessboard is just 64 times 63 times 62 and so on. And for the last one, you should have 57 possibility that comes from 64, the number of squares, minus 8, the number of rooks, plus 1. So eventually, that gives you the total number of configuration, and you notice that it's an example of arrangement without repetition. So arrangement because the order is important, because we assume that the rooks are distinguishable and we put them sequentially, and without repetition because we cannot choose twice the same square. So now let's redo the same thing, but making sure that the rooks are not on the same horizontal or vertical line. So for the first one, we again have 64 possibilities. So let's put it here, for instance. And now, to show you that to count the total number of possible ways you can put the second one, you see that this second one cannot be on this column here or on this row. And so to insist on that, I'm going to use the yellow pieces of the game to show you the positions that are not allowed for the second rook. Okay, so now we have a new configuration of our chessboard. with the first rook here, and the yellow pieces show you the positions that are not allowed for the second rook. So now for the second one, we can put it in any of those available squares, and the total number of squares, in fact, you don't really need to count that number. You can find a simple trick to know what's this number. Once you remove those two lines from the chessboard, you end up with 4 quadrants, and when you put the 4 pieces of the quadrant when you put those 4 pieces together, you end up in fact with a smaller chessboard with 7 by 7 squares. So that means that in this video, the number of squares that are available that you see is in fact 7 times 7, which is 49. So you have 49 possibilities for the second rook. And well, you understand after what happens, what's the pattern. You just have to remove this column, remove this line, and you end up with different pieces again that you can put together, and you end up with a 6 by 6 chessboard. So 36 squares. That's the total number of ways you can put the third rook. You have 36 possibilities. In general, the total number of ways you can put those 8 rooks sequentially, so assuming that they are distinguishable on the chessboard, is going to be 8 times 8 times 7 times 7, so 8 square times 7 square times 6 square times 5 square, and so on up to 1 square. So now let's go back to the board to write this, to turn this into equations. So to write this into equations, so let's introduce our event. So let's say A is the event that, let's say, no 2, and I'm going to insist on the fact that when we were counting the number of possible configurations, we assume that the rooks are distinguishable. So I'm going to say no 2 distinguishable rooks on the same line. So again, by same line, I mean not the same horizontal or vertical line, okay? And so, of course, we'll see that when we assume that the rooks are identical, okay, not distinguishable, but identical, in fact, even if the counting process is different, the probability, again, is going to be the same. So in this case, summarizing what we did, we get that the probability of A is just equal to, so we said that the total number of ways we can put those 8 rooks on the chessboard with no restriction. So when we do that sequentially, we have again 64 possibilities for the first one, 63 for the second one, and so on. So eventually we have to divide by 64 times 63 and so on, and we go up to, I'm going to write 64 minus 8 plus 1, okay, just to insist on the fact that we have here an example of arrangement without repetition. And then we said at the opposite that the number of ways we can place the rooks in such a way that they are not on the same horizontal or vertical line is going to be, so we start with a 64, but then for the second rook, we have only 7 times 7, which is 49 possibilities. So 49, then 6 times 6, 36, and so on, up to 1 times 1. That's 1. You can simplify this expression, and then eventually you find that, so this denominator can be written as 64 factorial divided by 56 factorial. So it becomes a 56 factorial here divided by 64 factorial. The numerator is just equal to So you can put in factor those squares, so it's 8 squared times 7 squared and so on. So eventually you end up with exactly 8 factorial squared, okay? So you have this times 8 factorial squared. Now, you can observe that if you look at the product, the sum of those two ones, you get exactly 64. And so, sorry, I forgot a square here. So if you look at the product of all these, you forget the square. So this times 8 factorial, because 56 plus 8 is equal to 64. That's exactly 1 divided by 64 choose 8. And so eventually you end up with this answer, 8 factorial divided by 64 choose 8. So that's one possible simplification. And if you do this calculation, you would get that the answer is about, so it's 9.109 times 10 to the minus 6. So of course the probability is very small. So you see here we did the counting process using for the total size of the sample space arrangement without repetition. That's the denominator here, and that's in the case where we assume that the roots are distinguishable. But again, clearly the fact that we assume that the roots are or not distinguishable should not affect that probability. So now to convince you of this, we are going to redo the problem, but assuming this time that the roots are identical, in which case the total number, like the size of the sample space, is going to be much smaller. But it turns out that the number of outcomes in the event A is going to be also much smaller and reduced, in fact, by the same factor. So we eventually get exactly the same answer. So for that, let's go back again to our chessboard. So back to our chessboard, let's see now how we can put those 8 rooks on the chessboard, but assuming that they are identical. So identical doesn't mean that, means that instead of doing things sequentially, now we do things simultaneously. And so the total number of ways you can put those 8 ones is just, well, same as before, but now the order in which we put them does not matter. So that's exactly the total number of choices of 8 squares from a set of 64 squares. So that gives you 64 choose 8 possibilities. So you see in particular that in this case, assuming that the rooks are identical, so again, meaning that you do things simultaneously instead of doing things sequentially, implies that the total number of possible configuration, which is the cardinal of omega, is going to be different. Now we have, instead of an example of arrangement without repetition, we have an example of combination without repetition. So now to count also the total number of possible configuration in such a way that the rooks are not on the same line, but thinking again in terms of choosing simultaneously 8 squares that are not on the same line, horizontal or vertical line. So let's redo things, and in fact I'm going to do things sequentially, but not sequentially thinking of the rooks, but sequentially thinking of the column of the chessboard. So why is it possible? Well, that's because there are exactly 8 rows and 8 columns, and that's also equal to the number of rooks. So this means that in fact the event that no 2 rooks are on the same horizontal or vertical line is the same as the event that each line, horizontal or vertical, contains exactly 1 rook. So that means that this first column should have only exactly 1 rook, this one only 1, and so on. So that's how we are going to identify the total number of ways we can choose 8 squares simultaneously, but in such a way that no 2 squares are on the same line. So For the first square in the first column, we have again 8 possibilities. We have 8 possibilities. And then I'm again going to use those yellow pieces here to show you what are the forbidden position for the next squares. So for that, clearly, we cannot put anymore a red piece on this line. So I'm going to put yellow pieces here to show you that those places are not allowed anymore. Okay, so now we have a new configuration like this. We have the first rook here. All the yellow squares are not allowed anymore. And so for the choice of a square on the second column, we now have 7 possibilities. Let's say this one. And again, I'm going to use yellow pieces to show what are the forbidden places for the last 6 columns. And then you see that for the third one, you have exactly 1, 2, 3, 4, 5, 6 possibilities. And so on. So now I guess you understood the pattern. So if we recap, we said that assuming that the rooks are identical, in this case, instead of doing things sequentially, we do things simultaneously. And so choosing 8 squares from a set of 64 squares, it's exactly 64 choose 8. That's an example of combination without repetition. Without repetition because we cannot choose the same square several times. But you see also that to count the total number of ways, you can put those 8 rooks in such a way that no 2 of them are on the same vertical or horizontal line. The total number of possibilities is exactly 8 times 7 times 6 times 5 and so on. So that gives you exactly an 8 factorial. So now, again, let's go back to the board to write that into equation. So to write what we just saw in equation, now I'm going to introduce another event that I'm going to call B, even if in fact the fact that rooks are distinguishable or identical, even if this does not affect the probability of the event A, just to convince you, I'm going to just give another name to this event, but then in the context where the rooks are identical, and you will see that the counting we just did gives us the exact same answer. So now we call B the event that no 2 identical rooks are on the same line. So we saw that because now we assume that the rooks are identical, indeed the total number of possible configuration, so the cardinal of omega, is going to change. Okay, so the counting is not the same, and instead of that number that we got before, I mean before the size of the sample space was 64 factorial divided by 56 factorial times 8 factorial. No, just this one, sorry, 64 factorial divided by 56 factorial. Now instead we have, we saw that we have to choose 8 squares from a set of 64, so that just a 64 choose 8. That's exactly the number we got here before after simplification. And so here we have to compute P of B. You start by writing that this is the total number of outcomes in the event B divided by 64 choose 8. So you see now that we have much less possible configuration, assuming that the rooks are identical, because now if you exchange, if you do any permutation of the 8 rooks, you are not going to change your choice of 8 positions. While in the previous case, assuming that the rooks are distinguishable, then exchanging them means that you exchange colors, let's say, and you create a new configuration. So now in the second case, we saw that to count the number of possible configuration. The goal was to choose one of the 8 squares in the first column. We have 8 possibilities. And then for the square we choose in the second column, we have only 7 possibilities, and then 6 and so on. So eventually, here you have an 8 times 7 and so on, and you go down to 1. And so this is 8 factorial divided by 64, choose 8. Conclusion, you see we get the same number, and so P of A and P of B are in fact the same. This is that number, and so conclusion, of course, if you think of the prime as a counting prime, a combinatorial prime, you indeed need to know whether the rooks are distinguishable or not to look at the total number of ways you can put them on the chessboard in such a way that no 2 of them are on the same horizontal or vertical line. Now, if you indeed look at the prime from a probabilistic point of view, and the goal is to compute the probability of those events, you see that assuming that the rooks are distinguishable or not does not change the probability. In one case, you have to you do some counting using arrangements, while in the second case you do the counting using combinations, but eventually you are going to reduce the number of outcomes in your 2 events by the same factor, and so eventually you get exactly the same probability.